Good evening. Welcome after a long time, seeing you for the very first time. Today is going to be the very last class, right, for the semester until we start our revision classes. Right. Now, this is what's going to happen during this period from now on up until, let me say, we finish submitting all the assignments and so forth. I want you to start doing all the exam papers or past exam papers so that you are already preparing for that. So you can send them through, and then we can, even during this time, arrange sessions where we can just say, next week Friday, let's meet and let's have a discussion on such, even before the revision class. Because I understand that during the revision period, things get tense and there's a chance of things slipping through. So before the pressure starts piling up, it is always better to start now. Right. Now, without much further ado, let's move into today's content. Right, we're going to be looking at post machines. We've already started looking at post machines. Post machines starts looking at Turing machines, Turing machine, and also we also have NPDA. So these are post machines. So, and then we need to know as well that a 2PDA is equals to a Turing machine. So there's a theorem that specifies this. So we say as long as we've got two stacks, we're able to mimic any machine that can generate any function. Right? So that is the power of post machines. So post machines are able to accept regular languages. They're able to accept context-free languages and also non-context-free languages. So they go beyond context-free languages. That's fair and fine. Now, looking at these two machines, right? We have seen how each of them individually work and how they go beyond, one without a stack, the other with an additional stack. Right. So let's get into the details. We have what are called recursive languages, right? Let me start by saying so far we've done regular languages and context-free languages, right? What goes beyond the scope of regular languages? So we have what are called recursive enumerable languages, right? So we say a language L is recursive enumerable, right? Or recursively enumerable if there's a Turing machine T that accepts every word and either rejects, which means crashing, or loops forever for every word in the language L and L complement. Right. So every word that is not accepted is either rejected or looped. Every word that is accepted is by the Turing machine belongs to the language. All that is not accepted will either find a reject state or will find a loop state. Right. So this is a class of languages called recursive enumerable language. Now we can proceed and check as well. We have got another language which we call recursive. So I put this, mix this up. So if I look at this, we call these ones recursive languages. So recursive say they do not have a loop state. Recursive languages do not have a loop state. So that is the difference of a recursive enumerable language in the recursive language. In a recursive language, we only have accept and reject, no looping. Either you accept it or you are rejected. So when we see this, we see that recursive languages, if you look at recursive languages, these languages are a subset of recursive enumerable languages. Why? The recursive languages are a special recursive enumerable languages where loop T is an empty set or does not contain anything. So that is a recursive enumerable. It is a subset of recursive. Right, now given this newfound information, we see that we now have two languages that have emerged. So one is a recursive, the other is recursive enumerable. Recursive enumerable. So these are the two languages that have emerged. And with their emergence, we want to see where their position lies in terms of regular languages, and context-free languages. But we can already have a guess to say a to the power of n, b to the power of n, a to the power of n, right, can be accepted by a Turing machine, right? Accept t, we can never accept t being that, and anything else being rejected. So definitely we see that our regular languages should sit here, and then we have context-free languages sitting there. Then we seem to have a language on top which is recursive, right? And then after recursive, we seem to have another one on top which is recursive enumerable. So it's recursive enumerable, RE for recursive enumerable. So since we are having this, since we seem to be having this, it is also important that we recognize this hierarchy, right? How do we do that? So we'll see later on how we're going to do that. Now, I mean, when I say later, we're going to discuss what is called the Chomsky hierarchy. So very soon you should be able to see how it works. Let's look at some theory. It says, theorem 60 says, if a language is recursive, then its complement is also recursive. So now, because recursive only has L and L complement, right? So we can complement recursive, right? The complement of a recursive language is also recursive, right? So that is one of the properties of recursive languages, right? Now, not only do we stop there, we see that if L is recursive enumerable and L complement is also recursive enumerable, then L is recursive. The only time, or what this is trying to say, is recursive enumerable languages are not closed under complementation. Meaning to say, the complement of a recursive enumerable language is not also recursive enumerable. So then the way they portray, they say the only time that a recursive enumerable language or the complement of a recursive enumerable language is also recursively enumerable is when L is recursive. Because we know recursive languages are a subset of recursive enumerable languages. If we have got two Turing machines, T1 and T2, then there exists T3 such that it accepts the union of these two languages. So what we are saying is, given a Turing machine or any language accepted by a Turing machine, right, the union of any language accepted by a Turing machine, if it is recursive or recursive enumerable, this is what it then goes to mean. The union of two recursive enumerable languages is also recursive enumerable. The union of two recursive languages is also recursive. So that is what it means, right? So then let's look at the next one. The intersection of two recursively enumerable language is also recursively enumerable. The intersection of two recursively enumerable languages is also recursively enumerable. So recursive enumerable is closed under intersection, right? So because by deduction, we know that recursive languages are also recursively enumerable. So recursive languages are also closed under recursive, also closed under intersection. We're going to look at what are called code word languages. But before that, I'm gonna come back to this. I want to start for us to look at some of these definitions that are here and make sense of what we were just going about discussing. So we have what is called the universal Turing machine. This is a very big definition to have and a very big definition to claim, right, or to understand. But let's understand what it says. It says a universal Turing machine, otherwise known as a UTM, is a Turing machine that can be fed as input a string composed of two parts. The first is the encoded program of any Turing machine, followed by a marker. The second is a string that will be called data. The operation of a universal Turing machine is that no matter what the machine T is, and no matter what the data string is, the universal Turing machine will operate on the data as if it were a Turing machine. Right. So if T would have crashed the data, it will crash. If T would loop forever, it will also loop forever. If T would accept, then the UTM would do so. Not only that, but the universal Turing machine will leave on its tape the encoded T. The encoded T, the marker, and the contents of what T would leave on the tape if it accepts any input string. Right. All of this, what it is trying to say is to say any machine that would behave as a Turing machine would, is a universal Turing machine. Universal Turing machine. So in short, this is a short definition of a universal Turing machine. A machine that would accept words as a Turing machine would, reject words as a Turing machine would, and loop words as a Turing machine would is called a universal Turing machine. It should behave as a Turing. We have what is called the Chomsky hierarchy. So the Chomsky hierarchy is very important in the sense that you see that it summarizes the whole theoretical computer science in a nutshell. So we saw here regular languages, we dealt with them, dealt with regular languages. We looked at context-free languages, and then here, after this, we did not know what this was. Right? So we've got another set, then we've got context-sensitive, then we've got recursive languages, and we can only assume that this, where they say put Matheson and Allen, is also what we can call a recursive enumerable, because we know recursive languages are a subset of recursive enumerable. So that is a description or a short description of what the Chomsky hierarchy is. Right. So this is what the Chomsky hierarchy is. And usually it is better for you to be able to put this in your own words. When asked what is the Chomsky hierarchy, right? So there is an order, definitely, right? So these are the keywords that you can use. There is an order, right? So and in this order, we see that we are going to have more and more languages for each. So it is an order of languages, number one. So it's an order of languages from smallest to largest. So we've got smallest. So it's ordered of languages ranging from smallest to languages to largest, giving descriptions and behavior of each. So we've got grouping by behavior occurring. A few of the cases that you can use to describe it as. Right. Then for a full definition, because this is a lengthy one as well, but what I prefer is that you put this in your own words. Right. For a full definition, you see there's one that will be found in the exam papers that will be given. But in a nutshell, we are trying to describe what we've just been doing, right? It is an order in which languages are given with respective of their behavior, right? So that's Chomsky hierarchy. And then we also have another definition here, computable function. What is a computable function? Essentially, this is generally a function that they're asking. If you know what a function is, you should know what a computable function is. Right? So because the whole definition of this, the whole concept of a computer is based around functions. Right? So what do we know about a function? So here they say now blah blah, we find out what a computer is. Those expensive boxes, right? So here it's not really given, but they ask usually about the definition of a computable function, but we can define it as follows. We say a computable function, I'll demonstrate it, and then you can have a formulated definition on your own, right? So what is a function? We know a function when we have, say, we have got the domain. So if we have got A, B, C, and we've got 1, 2, 3, 4. If we have got these, right, we can say a function can be 1 to 1, 1 to 1 to 1 is a function, right? Many to 1 is a function, so many to 1 is a function. Then what is not a function is something like this. Something that maps one input to two multiple outputs, then this is not a function. So from the definition of functions that you already know, this is what we're getting. 1 to 1 is a function, many to 1 is a function. Right? So now if we look at this, if we want to give the definition here, we'll say a computable function, right, is one that maps, this is one that maps, number one, each element of the domain, right? Or we can say that uniquely maps each element of the domain, right? So what is a computable function? It is a function that maps each element of the domain to a unique element in the range. So this definition from past, I hear that when we say uniquely, some are not comfortable with the word unique. So the uniqueness is in the sense that I'm going to take an element from the domain, I will map it to a unique element in the range. So it's going to be mapped to a unique element in the range, to exactly one in the range. So one input is mapped to one output in the range. Right. So one of the questions that they can ask here, what that they usually ask is to say, you are given this function. You are given this function to say, they can give you to say, for x is greater than 5, you are going to print, this will give you 0. For x is less than or equal to 5, you print 1. And then they say the domain, they give the domain to be from negative infinity to infinity, right? So if you go into the domain, you realize that all the integers, right, x is an integer such that that happens. If you see this, you realize that on a domain of integers, all the domains are catered for, or rather not all the domains are catered for, right? Not all the domains are catered for. So if not all the elements of the domain are catered for, then it is not a function. What do I mean not all the elements? I'm missing 2, 3, and 4, and 5. So these are not mapped for elements of integers. These are not mapped, right? So now, however, if we say this to be 5, then this becomes a function because all the elements are on all integers are mapped, right, to an unique output. Then people ask, why is 0 unique when many elements are going to it? The answer is the following. regarding the element in the domain, from the element in the domain's perspective, it is going to one unique element. It is going to one unique element. And this makes it unique to it. The fact that someone else is also going to it, this element will not see. It will see itself going to one unique element. Right. So that is a computable function. Then another definition we ought to know is that of, it's not a definition per se, it's called Church's thesis. Right. So Church's thesis, and I say thesis, and it is said as thesis because it has not yet been proved wrong. Right. So a thesis is something that remains true up until proved wrong. And Church's thesis says, the Turing machine is the ultimate computer. Ultimate computer, meaning it can compute all functions known to men. Now, if this is true, then truly the Turing machine is a very complicated, very big machine, right? True up until this point, and remains a thesis because there is no decidable way of proving whether or not this Turing machine is the ultimate machine. Right. So that is Church's thesis. So we may come across some definitions as we read, but just go through these ones. So to properly go through these definitions, you can go through chapter 22 to chapter 26, I believe. But most of the stuff you're going to leave. So your KTM, your variations of a Turing machine, you are not going to be doing. So you can read them, don't draw them, just understand what they are in the event that they ask about them in the exam. But that is rarely versed in it being asked. Right. Now, let's come back to one section that we skipped. Code word languages. Right. So code word languages bring about the topic of encoding. Right? How do you encode? So now if you've got DSTV, you've got what you call a decoder, right? So your decoder is decrypting or decoding, as the name sounds. It is decrypting an encrypted or an encoded signal so that it can be played on your TV, it can be played on your whatever terminal that you're playing it at. Right, so encoding is the process of sending information in such a way that you do not end up losing that information. You do not want to lose this information. Right. So how do we go about doing that in such a manner? So the way to do it is to say, then send the key or whatever the receiver, the decoder has got a key, and then so we've got the sender, we've got the receiver, we've got the encrypted message. So this and that need to be in sync. A very simple one that we can think of is your electric gates that are opened by remote or remote controlled gate. Right, if you just go and buy a remote and then come and try and press it, it is not going to work. It needs to be in sync with your gate, right? So for those of you that know, you have to program the remote before you can use it, right? So now, because out of scope, but they use what are called frequency, or what's called frequency hopping, so that when you press the button, it hops to they both do it, hops to a new frequency, that, so that when you come next time, it will be in sync. When you use it next time, it's going to be in sync again. When you use it again, then they hop to another, so that you are not going to be using the same frequency to do that. Otherwise, it is easy to hack. Right. So now that is a simple case of encoding, transmitting a message between two objects. Now, funny enough, Turing machines or the modern day computer were created to decode messages during the time of war, right? Second World War, around about there. I'm not going to go into the history of Turing, but this is what it was meant to do, to decode messages, right? But today we are going to be looking at the code word language. How would we send information about a Turing machine to someone else? Right. So if you wanted to do that, we can look, for example, at a picture. A picture is going to be a matrix with zeros, one, zeros, one, zeros, one, zero, one, zero, one, 1, 1, 1, 1, 1. Right. So if it is black and white, zeros will mean absence of color, and white will mean white. So that's 0 and 1. Now, in that case, right, we can transmit this line by line. We can encode this line by line, 0, 1, 1, 1, 1, 1, whatever the case is, in a serial bus. So you know, is USB, universal serial bus. So in a serial bus like that, in such a way, when it is received by the sender, they will know that this is this picture. When you send using Bluetooth, when you send using whatever case you are sending it. Right. Now, we need to find a way of encoding our Turing machine so that we can also send it to the next person. They can decode it and roll the exact same Turing machine. And there is such a way. Right. The first thing we need to do, however, is to convert it to a summary table. For those who are seeing the summary table for the first time, is we are writing what is happening in this Turing machine. If we say 1 is start from number 1 to number 2, we have got a B, and then R. Right, number 2 to number 2, we have got a B, and then R. Number 2 to number 3, we have got an A, and then R. Number 3 to number 3, we've got an A, and then R. Number 3 to number 2, we've got a B, and then R. Number 3 to number 4, we've got now, and L. So this is a summary table. All I've just done, I've given a summary of what each transition is doing, right? The transition from 1 to 2 is reading a B, writing a B, and moving to the right. Transition along 2 or looping around 2 is doing the exact same thing. Right. Then after converting the summary table, right, we need to understand this, right? So we need to understand this part to say we can encode as follows. We can encode as follows. An A uses a B uses AB, a now uses BA, a hashtag represents BB. So if you have got an A, it's now going to be converted to AA. If you have a B, AB, now it's going to be a BA. And the hashtag will be represented by BB. The movements are going to be encoded by left A, right B. Right. So those are the movements. Now, when we come back to this one, after we've converted to a summary table, right, we want to ensure that this table is converted using the code word that we learned. So we learned that an A is represented by AA, B by AB, now by BA, and then hashtag by BB. So this is what our machine has. So and we've got left represented by A, right represented by B. So I can convert this summary table to, so I have 1 to 2, I have got B is AB, AB move to the right is B. 2 to 2, I've got AB, AB move to the right it's B. 2 to 3, I've got A, which is AA, A, which is AA, move to the right, which is B. 3 to 3, I've got A, which A represented by AA, A represented by AA, and B, which is to the right. Then 3 to 2, right? 3 to 2 goes to with a B, so that's AB, with a B, that's AB, move to the right, that's a B. Then we also have 3 to 4 is now, which is BA, now BA move to the left, which is an A. So we have converted from here to there. Then the next part is as follows, right? The 1s and 2s are not going to be sent like that. If you want to represent 1, you're going to represent it with 1A. 2 is going to be represented with 2A's. 3 is going to be represented with 3A's. So in a nutshell, the number of A's represent a number, right? The count of A's represent the number it is representing. So 1, 2, 3, you have 4, and so forth and so forth. Right. Now, given this, we can then come and say this was from 1 to 2, so we have got 1A, 2A's. Then 2 to 2, we have got 2A's, 2A's. Then 2 to 3, we've got 2A's, 3A's. And we've got 3 to 3, 3 to 3, we've got 3A's and 3A's. And then 3 to 2, 3 to 2 is like that. Then 3 to 4, we're going to have 1, 2, 3, 1, 2, 3, 4. So this is going to be the table in code word language. Right. But it is not yet in its serial form. So we need to have one long serial number that we should be able to transmit. Right. So for us to do that, we do the following. Right. If we were to take this row, it would be A, B, B. Right. This, if we read from the last, we know that this is right, this is B, this is B. But here we do not know whether it's 2 to 1 or 1 to 2, right? Which is important, 2 to 1 or 1 to 2. So in order to make that distinction, every time we write the code word language, you're going to put a B and a B as a spacer here, or a demarcator. So we're going to put A, then B, then AA, then B. You're going to put AA, then B, AA. You're going to say AA, then B, AA, then B. So this is going to be our spacer or demarcator. So we're going to say A space AA space AB, AB, B. Now I'm going to come, when I start from here, I'm going to say 1 space to 2 space with a B, with a B, with a B. Because this part is always going to be carrying 5, it is constant. Then I start again, AA space AB, AB, B. Then AA space AAA space AA, B. Then this one, we've got AAA space AAA, so we need 3. then space, then AA, B. Then we're going to have AAA, B, AA, B, AB, AB, B. Right? Then we're going to have the last one AAA, B, AAA, A, B, BA, BA, A. So when you receive this code word language, so this is the code word language is given by, you come and say, okay, 1 to 2, B, B, right. Then 2 to 2, B, B, right. Then 2 to 3, A, right. 3 to 3, A, right. 3 to 2, B, right. Then we've got 3 to 4, BA is now left. So you can interpret it using the given key, or deconstruct it using the given key. So this is the code word language. Now, lastly, we have seen before when there is talk of this one, we've got Matheson and Alan that we have not yet defined. So Matheson says, if you look at this, right, we say a language belongs to Matheson, the language of the Turing machine it represents, right, is not accepted by the same Turing machine. So in a nutshell, we are saying a language belongs to Alan if it is not accepted. A code word language belongs to, or a language belongs to Alan if its Turing machine does not accept its code word language encoding. So in this case, we are saying if we were to pass this word into this Turing machine, if we find that at the end of the word we're in a hold state, then we know that this Turing machine, this language is not in Alan. Right? If it is in Alan, it means it has to be rejected by this machine. So here we started with an A. So we started with an A, but our language starts with a B. Therefore, it is rejected there and there. So it belongs to Alan. Right? Matheson, however, says Matheson, a language belongs to Matheson. So the opposite is true for Matheson. So the full name for Turing was Alan Matheson Turing. So this is all that there is to it. Alan, the code word language is to be rejected by the machine it represents. Matheson, the code word language is to be accepted by the Turing machine it represents. So for some reason, we see that there is more power, or we've got more, Alan is bigger than Matheson. So that is all for today. So I'll stop there, and then I'll wait for any questions that you might have so that we can go through them together. But for in terms of the classes, this is where we